In this video, we're going to run the both integrators in Matlab and just show the results for the ODE45 and the Runga Kutta, and then we're going to compare the outputs to each other to see how close they are. So right now we're just going to focus on user inputs for the simulation. So we start with what I call the app type. It's either going to be Matlab or Octave. Now, as mentioned in the article, if you don't have Matlab, you can download for free a copy of Octave and run this same code. Octave has an ODE45 integrator function as well, but in this case we're running in Matlab. We're going to set the forcing function to type 1, which is a lower frequency. For the integration type, we're going to do the ODE45. Next time around we'll run the Runga Kutta and set it to 2. We're going to set the variable time step option to 1, which means that the ODE45 is going to vary the time step depending on the internal algorithm to optimize the search space in terms of finding a solution. Now these are just basic parameters for the simulation. This is start time, end time, and the time step, if the time step is being used, which in this case it won't. These are the system parameters: mass of the object, damping constant, spring constant, and then these are the initial conditions: position and velocity. Now this is a XYZ 3-element state vector. We're only running a single degree of freedom, but I leave this open for future use if you're going to do a 3 degree of freedom type simulation. But anyway, so let's go ahead and run it. Oh, one thing I was going to mention, when this is done, you'll see over here that it generates a .mat file which contains the trajectory information, which can later be plotted when comparing both the results of both integrators. So let's go ahead and run it. Okay, so this, as you can see, this is the time step profile, and it varies quite a bit because the frequency of the force is very high right here. There's a lot of changes in a short amount of time, so the time step needs to be really small to accurately generate or accurately integrate the trajectory. Then as the forces settle out, the time step can get bigger. And here are the plots of the actual trajectory state vector. This is position and this is velocity. And as you can see, the .mat file was generated, which will be used when we do comparison tests. And this trajectory simulation was generated in about 0.04 seconds, so it's not slow. Now we're going to switch to the Runga Kutta with a fixed time step. Okay, and we'll run that. Alright, now you can see the time step was fixed. It's actually at 0.05 seconds. I should have changed the scaling on here. And again, here's the trajectory profiles, position, and velocity. They look similar, but we really don't know how close they are at the moment. But as you can see, the other .mat file was generated, which will be used for comparison purposes. Okay, so now we'll run the function that actually compares. It pulls both of these in and then plots the data together, and we'll see how they do. Okay, so right here we have the position and the velocity for both the ODE45 and the Runga Kutta integrators, and as you can see here, they're pretty much right on top of each other. One is blue, one is red, and you can see a little bit of blue, but they're very close. So this is good. Both integrators agree, and that's good news. It helps you balance things when you're trying something new. Maybe have both integrators just to make sure that you're using the right time step and so on.